Okay. Welcome back, everybody, for the last lecture for the Kavli Asian Winter School 2022. Of course, we'll have the tutorial sessions over the weekend, but this is the last lecture in the series. And this is the last of Surjeet's lectures as well. So over to you, Surjeet, who's going to tell us about opening up the gravitational wave spectrum.
Yes, thank you very much. In my opinion, right, I think the discovery of gravitational waves that happened in the last few years experimentally is one of the most important scientific advances of the last, I would say, several decades. It's the sort of thing that many centuries from now, humanity will look back upon and understand how important it was. And this is for a very fundamental reason. Pretty much everything we have learned about the universe so far has been by studying various forms of light. Starting from Galileo's discovery of the planets, the moons around Jupiter, which overthrew several centuries of Ptolemaic thought, through the continuing discoveries that we keep making every few years in various forms of light, right? So pretty much every frequency band of light that we have explored, we have found new discoveries. So I think it's not unreasonable to think that something similar is likely to happen for gravitational waves as well, simply because this is now new eyes with which we are actually looking at the whole universe. So of course, to begin with, we know there are many known sources of gravitational waves that don't emit light. For example, mergers of black holes, mergers of compact astrophysical objects such as white dwarfs and neutron stars. And at the end of the day, if you really want to understand the physics of the very early universe, you pretty much have to use gravitational waves, because even though we have learned a lot about the universe by studying the cosmic microwave background, as we all know, as you go back in the history of time, the universe gets too hot and too dense for light to freely propagate. So if you really want to understand what happened to the universe prior to the era of recombination, you cannot use electromagnetism to learn about it. You have to use gravitational waves, right? So it's extremely important, therefore, to try to understand how we can build upon the extraordinary successes of LIGO. LIGO operates in trying to find gravitational waves in the frequency band from about 10 hertz to about 1 kilohertz. That's what LIGO is maximally sensitive to. But there are, of course, other frequency bands of gravitational waves as well. And the question really becomes, what can we do observationally to try and discover gravitational waves in these other frequency bands? Okay. So that's the content of this talk, basically. And let me just give you the 1-minute summary of how you're trying to detect gravitational waves. If someone wants to detect gravitational waves, here is the main thing you want to do. You take two objects, you separate them by some distance L, then you allow the gravitational wave to do its thing. And what the gravitational waves do is that they cause the distance between these two objects to modulate, okay, by some amount. And the difficulty in detecting gravitational waves is because even with the brightest sources of gravitational waves that we are talking about, from mergers of black holes, things of this kind, if you take two objects and separate them by something like, 1,000 kilometers effectively, and you look at some of the brightest sources of gravitational waves in the sky, they will cause length changes between them that are as small as 10 to the negative 18 meters. That is essentially a factor of 1,000 smaller than the atomic nucleus, right? So the challenge in detecting gravitational waves is that you have to measure an incredibly small length change of two objects that are separated by gigantic distances between them. And so technically, from an experimental point of view, what this means is that you need techniques that are able to solve two problems. The first is precision sensing. By precision sensing, I basically mean what technology can you use that is able to measure a length change that is as small as 10 to the negative 18 meters. You need some technology that is so precise to be able to measure such a very, very small length change. The second thing that's also equally important is essentially isolation of these objects from the environment, or some kind of vibration isolation, right? So let's say you take these two objects, you separate them by something effectively like 1,000 kilometers. You're trying to measure a length change that is as small as 10 to the negative 18 meters. So even if you had a technology that could measure the distance between them that accurately, right? You also have to ensure that these two objects are only moving due to gravitational waves at this very, very incredibly small level. Because of course, if someone else came in and moved this guy around by a distance that is larger than 10 to the minus 18 meters, obviously what you will then be seeing is not the effect of the gravitational wave. You will be swamped by the noise which this environment created around you. So basically, you require in concert precision sensing and extraordinary vibration isolation. So let's look at the gravitational wave spectrum. So this is basically the statement of what do we expect the sky to provide us, right? We have various astrophysical sources of gravitational waves that people expect. And we're basically asking, if that's what the world is providing us, how sensitive do we need to be? So this is purely a statement about astrophysics as opposed to any technology going in there. So here's what the astrophysics tells you. On the x-axis here, I've plotted the frequency. Basically, two stars or whatever are going around each other. They're going out at a certain frequency, and the gravitational waves roughly come out at twice that frequency, right? So that's the frequency here on the x-axis. On the y-axis, I've plotted the characteristic strain. The characteristic strain is basically the expected amplitude of the gravitational wave on planet Earth, right? So somewhere in the universe, something is happening. They're producing gravitational waves. There's a strain from the gravitational wave that we're able to measure locally on the Earth. And this is the expected strain from various astrophysical sources. And I've plotted various existing experiments like LIGO and Virgo, as well as pulsar timing arrays over here, and also the proposed LISA experiment that's somewhere over here. Okay, so LIGO operates at a frequency between about, let's say, 10 hertz and a kilohertz. That's basically the peak frequency of LIGO. Pulsar timing arrays, they're essentially working around nanohertz or so. I'll tell you what these are in a bit. We already talked about it earlier when we talked about dark matter. But these experiments operate at a frequency of around a nanohertz or so, 10 to the minus 9 hertz. The LISA experiment, the peak sensitivity for LISA will be around a millihertz or so. Okay, that's what LISA is supposed to actually exist. Now, if you look at this plot, you notice something very interesting, which is that if you want to go to a higher and higher frequency, right? That is, if you want to go to the right of my plot here, you notice that the amplitudes of the gravitational waves are actually considerably lower, right? So if you have to measure gravitational waves at a kilohertz, you better build a detector that is sensitive to a characteristic strain of around 10 to the negative 22. Okay. Whereas if you want to go to the left of this plot, if you want to go to lower and lower frequency, you notice that the expected gravitational wave strains are considerably larger. So for example, if you want to detect gravitational waves at a nanohertz, you are not looking at strains around 10 to the minus 22. You're looking at things that are more like 10 to the minus 16. Okay. So why is that? Well, that basically has to do a lot with the expected astrophysical sources in the sky. When you're looking at gravitational waves at a kilohertz, you're basically looking at mergers of, solar mass black holes, 10 solar mass black holes, those kinds of guys. While at very low frequencies, you're looking at mergers of supermassive black holes, extremely large black holes. So what's going on here is that if you think about the physics of gravitational wave mergers, you're basically saying I have two stars. These stars are going around each other. And of course, they're starting from very far away from each other as they're going around each other at very, very long distances. The frequencies of the gravitational waves are, of course, extremely small. And what's happening is that they go around each other. They continually emit gravitational waves. They keep falling closer and closer towards each other, at which point they start going around each other faster and faster. So as they go around each other faster and faster, the frequency of the gravitational wave keeps going up. Okay. Now, the highest frequency that you can attain in a merger is basically set by the physical size of the star. So if you have a 10-kilometer, black hole, which corresponds to a 10 solar mass, black hole, that would essentially take you all the way to frequencies of around a kilohertz or so, okay, or 100 hertz or so. While if you're thinking about a supermassive black hole is enormous in size, which means the two black holes will merge well before they can go to high frequencies. So the supermassive black holes that are actually extremely strong and powerful in emitting gravitational waves, their strains are extremely large, but they can never go up to high frequencies because the black holes hit each other well before they get anywhere to the high frequency where LIGO is looking at, right? So that's kind of what this plot really is telling you, is that at the highest frequencies, we're looking at smaller and smaller stars, and that is why the gravitational wave strain is considerably lower than what it is at lower frequencies, where the stars themselves are so huge and so powerful in mass that they're actually able to emit much brighter sources of gravitational waves, but yet the frequency is considerably lower than what it is over here. Now, what this tells you is something very important, which is that to go to higher and higher frequency, you need more and more precision. So then you must ask this question, why did LIGO spend 40 years, okay, building this incredibly difficult experiment to go after the lowest possible strain, right? If you look at this plot, naively, you might think, well, I need a lot less precision to detect gravitational waves at 10 to the minus 9 hertz because I only need to measure strains of around 10 to the minus 16. So why did these LIGO guys work so hard to get to 10 to the minus 22, right? Why do they do that? Well, the key challenge is basically that while it is true that precision, okay, you need less precision to go at nanohertz than you do at a kilohertz, what you require is stability, right? So this is the second part of gravitational wave physics we talked about. The first was precision, the ability to measure a very small effect. The second is stability. If you take two objects and you separate them and you are trying to measure the distance between them, you better ensure that the distance between them does not change by anything other than gravity, okay? Otherwise, you won't be able to see the gravitational waves. So what happens is that as you go to lower and lower frequency, even though the signal is brighter, when you're thinking about a nanohertz essentially corresponds to a frequency of around 10 years. So think about what you need to do. You got to take two objects, separate them by some distance, and then for 10 years, you have to ensure that the distance between them does not change by anything more than this incredibly small 10 to the minus 10 meters or whatever the strain actually corresponds to for 10 years, right? Obviously, that's incredibly difficult on planet Earth because all kinds of things change. So what you see from this plot is that as you go to lower frequency, even though you can use a less precise instrument, the difficulty really becomes from the point of view of stability. How do you ensure that the objects you're trying to measure are only moving due to gravity for the period of observation, which of course is very, very long now, okay? So that is the two challenges of gravitational wave detection. Are there any questions on this central idea? I'm happy to answer them if there are any. Okay, I guess not. So I'll move on. So here are the three technologies I'll talk about. All of this is basically, well, I mean, some of this is old and happening. Some of this is very new. I'm not giving you an overall overview in the sense that, I mean, a lot of that. Oh, so there's a question, looks like.
Yeah, so let me read it out. Shivam is asking, where does gravitational waves come from before recombination era?
Lie in the spectrum, yes.
Yeah, coming from before recombination era, lie in this gravitational wave spectrum.
Yes, good question. So it really depends a lot on when before recombination you're talking about, because recombination, of course, is an EV in temperature. So here's how it works. Okay, so LISA frequencies, okay, those roughly correspond to something going on at the electroweak scale, right? While LIGO frequencies would correspond to things that are even higher than the electroweak scale. So essentially, if you're able to go at LISA frequencies, you will be able to see gravitational waves that were produced at when the temperature of the universe was about 1 TeV. Okay, so and one can sort of linearly scale from that. So it is in fact the case that when you're actually probing gravitational waves in these frequency bands, you are getting a window into the very early universe. TeV scale over here, and whatever 100 TeV or something as you go to higher and higher frequency. All right, so I'm going to talk about three different ideas. The first idea I'll discuss is basically the use of atom interferometers to detect gravitational waves in the frequency band around 0.1 to 10 hertz. So that's an ongoing activity that I kind of created about 10 years ago, and there's lots of activity on that nowadays. These two other ideas are brand new. So one of them is the idea of trying to use asteroid ranging. We'll talk about what that is to look at gravity waves between a microhertz and 0.1 millihertz. The paper on this was just written about a couple of weeks ago. And the last idea is about astrometry, which is a way to detect gravitational waves at around a nanohertz or so, 10 nanohertz or so. So we'll talk about all of these. And I'll also briefly highlight how these other technologies work as we actually discuss why these new ideas are needed in these particular bands that we're talking about. All right, atom interferometry between 0.1 hertz to 10 hertz. So first of all, let me give you a science case. Why was it interesting to look at gravitational waves in a frequency band from about 0.1 hertz to 10 hertz? So the garden variety astrophysical thing that you want to look at in this frequency band is basically the mergers of white dwarfs. Okay, so mergers of white dwarfs are believed to be a primary source of type 1a supernova. So we talked quite a bit about supernova yesterday in the context of using primordial black holes to blow stars up. But of course, that is not the conventional astrophysical explanation. The conventional astrophysical explanation for how a type 1a supernova could go off, one of them is basically the fact that two white dwarfs can merge with each other. And when they merge with each other, they explode as a nuclear bomb. We don't know this is true. We don't know if this is what actually happens, right? Because we have never really observed something like this. But a gravitational wave detector would actually allow you to do that, because you'd be able to go and look in the sky. You'd be seeing gravitational waves being produced by your white dwarfs. Your gravitational wave detector can see it. And then you can, if you're able to make angular localization and you can point to the direction of the sky, you can predict when a supernova will go off, and you can go look it up. Okay, so that's why this is very important to do as a way for us to establish that type 1a supernova are actually being caused by these kinds of white dwarf mergers. Now, the reason why you can't actually see this in LIGO is because white dwarfs are pretty fat. They're about 10,000 kilometers in size. And so as we talked about, the highest frequency that you attain in a merger is set by the size of the star. So since a white dwarf is about 10,000 kilometers, when they actually merge, the merger actually happens in this frequency band from about 0.1 hertz to 1 hertz, as opposed to making it all the way to LIGO. So this is one of the major things one could look for if you had a detector operating at this particular frequency band. The second important thing is also about LIGO sources themselves. So all of these sources that LIGO sees at a kilohertz or 100 hertz, they will all have to go through lower frequencies before they get there, right? Because of course, these two black holes initially start off being very far from each other, and then they're continually emitting gravitational waves as they're falling in. So initially they begin at very low frequency, and they're sort of falling in and getting spun up faster and faster and faster. So as they're actually going towards 100 hertz, they'll of course go through this low frequency before they can get there. The reason why this is interesting is basically because if you ask how long does a source live at a given frequency, the amount of time it actually spends at low frequency is considerably larger than the amount of time it spends at a high frequency. So for example, the LIGO sources in the LIGO band, they only last about a few seconds, okay? But obviously as they're further and further away from each other, they last thousands of years in those low frequencies. So it turns out that if you look at the LIGO source, okay, that LIGO will see, it will spend about 1 week going through 0.1 hertz to 10 hertz before it actually makes it to LIGO. So think about how cool that would be if you actually had a detector operating from 0.1 hertz to 10 hertz. You can go and tell LIGO, look, a week from now, you will see something in your detector, right? That'll be very, very interesting. Not only is it just a coolness factor, there's also a very interesting astrophysical element of this, which is that this 1 week time that you basically have before you see the merger allows you to do very, very precise angular localization of this event, okay? So how do you do angular localization? Angular localization is basically done by some kind of triangulation, right? You basically have some detectors, 3 detectors operating. That's why LIGO, for example, has 3 detectors. It's why they want to build LIGO India, to get an additional detector in order to be able to triangulate where their sources are coming from, right? They see the same source at 3 different points in space, and then you can do some triangulation to figure out where the thing actually is happening. Now, if you think about triangulation, one of the things that really helps you in making angular localization is that you want to have your 3 detectors spread out by as much physical distance as possible, right? The longer the physical distance between your detectors, the more precise angular localization information you can actually get. Now, on the Earth, no matter what you do, the largest separation one can actually achieve is on the order of a few thousand kilometers set by the size of the Earth, okay? So when your source only lives for a few seconds, the most you can ever do on planet Earth is a baseline between your detectors that is order a few thousand kilometers. But now think about the fact that if you had a source that lasted 1 week, right? In 1 week, planet Earth travels a very large distance around the solar system, right? The Earth moves around the sun with a speed of around 10 kilometers per second. So in 1 week, it travels a much, much larger distance around the solar system than the 3 detectors that you can place on planet Earth, right? So when you have a 1 week lead time for this 1 week of observation time, you realize that you're able to actually achieve essentially degree scale localization of these LIGO events in the sky. Okay, simply because the Earth is moving over a big distance. And not only do you get degree scale localization, you also have 1 week to go and tell all of your electromagnetic observatories in the sky, tell them to go and point in that particular direction, because you're giving them 1 week advance notice for where something interesting is going to happen. So if you really want to achieve some kind of multi-messenger astronomy, operating an experiment in 0.1 hertz to 10 hertz would be extremely important to do that. Someone asked this question about cosmology. And in fact, 0.1 hertz to 10 hertz is actually a very, very interesting frequency band for cosmology as well, it turns out. And that is because if you're interested in finding gravitational waves from things like inflation, right? So inflation, unlike, let's say, a specific cosmological event that happened at a certain temperature, if a specific cosmological event happened at a certain temperature, you'd only get gravitational waves peaked around the Hubble scale at that time. But inflation, importantly, is supposed to produce a gravitational waves with equal power across a whole range of frequencies. Inflation is supposed to give you a flat power spectrum. That's one of the most important accomplishments of inflation. So when you get a flat power spectrum for inflation, there's a very simple mathematical fact that follows from it. So here is this quantity omega, which is the energy density in gravitational waves. Okay, that scales as the amplitude of the gravitational wave h squared times frequency cubed. Now in inflation, this quantity omega is constant. That's what it means to be scale invariant. Okay, what that means is that the amplitude of the gravitational wave is now inversely proportional to the frequency to the 3/2. Now here's a key fact, right? All gravitational wave detectors, they're actually responding to the strain of the gravitational wave. When LIGO is building a detector, they're looking for the strain of the gravitational wave and not to the power, which means that if you want to look at a source like inflation, you want to look at the lowest possible frequency at which you can see the gravitational wave, because that is where the strain is the largest. It looks like there's a question. Let me look at what that is. The weak observation time is about observing parallax or observing aberration. No, it's really more about it's not really, well, you can call it parallax if you want, but it's really more a statement about triangulation, right? So when you want to look at a particular source in the sky, what you're really looking at is the fact that I'm going to look at some signal coming from it, so say the gravitational wave phase, and I want to look at that signal at multiple locations and see how the phase is evolving. And that's how you fit out what location in the sky it's coming from. So the larger the separation between your base stations, the more accurately you can determine that phase. Okay, so switching back to this point here. So if you look at this formula, you say if you want to look at inflation, I want to go to the lowest frequency possible. That's what you learn from this. So then you say, well, why don't you go to the lowest possible frequency, 10 to the minus 7 hertz, 10 to the minus 9 hertz, right? Because obviously gravitational waves can exist everywhere. But the key point is that as you go to lower and lower frequency, say below 0.1 hertz, there's a very large background of gravitational waves being produced by all the white dwarfs in the universe. So these white dwarfs there's a large number of white dwarfs in the sky, because pretty much every star will eventually end up as a white dwarf. And white dwarf binaries all around the universe produce a huge background in gravitational waves, which will be much larger than the signal from cosmology. So if you want to really look at cosmological signatures of gravitational waves, such as inflation, it is extremely important to build a detector at the lowest possible frequency, where the strain is the largest, while still not being swamped by astrophysical backgrounds. So all of these white dwarf things will disappear around 1 hertz or so. So if you want to do something between 1 to 10 hertz, that is the best place to do cosmology, essentially. So that's why it's very important to build something in this frequency band. So why can't LIGO do this, right? Why, given all the exciting physics one could do, why can't LIGO do this? So let's briefly tell you how LIGO actually works. How does LIGO work? LIGO has these mirrors, okay? So each of these mirrors are separate. So they basically take 2 mirrors. Okay, so here are 2 mirrors. You separate them by something like 4 kilometers. And then you send a laser through those mirrors. And basically all you're doing is basically using the fact that the laser bounces from one mirror, comes back to the other mirror, and then you're doing some interference measurement, which allows you to measure the distance between these mirrors very, very accurately through an optical interferometer style setup. Now, if you notice, LIGO does not have just one arm, they have two arms. And you can ask, why is that? The reason is because whatever laser you're actually producing is a noisy instrument, right? You're trying to measure an incredibly small length change. Now, the laser is being produced by some equipment that human beings make, and the laser will have all kinds of noise, phase noise, frequency noise, all kinds of things. So the reason why they have two arms is basically because they take the same laser beam, it's split and sent around two different directions. So the same laser beam goes here, the same, and half of it goes here, half of it comes back here. And when you do a differential measurement, which basically is saying, let me compare the laser phase on this side versus the laser phase on this side. If I subtract those two things, you will find that any noise in the laser is completely common and therefore gets canceled. While if you look at the signal from a gravitational wave, when it actually expands space in one side, it contracts space on the other side. And therefore, when you do this differential length measurement, the gravitational wave signal is maintained while the noise in the laser gets canceled. That's why LIGO has two arms. So that's why they do it, to cancel laser phase noise. To tell you more about LIGO, what they effectively do is that they take these two mirrors, they're separated by about 4 kilometers, but the light undergoes 200 bounces as they go back and forth. So effectively, the effective arm length of LIGO is something like 800 kilometers, 4 kilometers times about 200 bounces. So that's roughly what they're actually using. So that is so much about the sensing part of LIGO. But that's not enough, right? These mirrors are obviously hung from the ceiling. And remember, we have to ensure that these two mirrors do not change, the length between them does not change by more than 10 to the negative 18 meters due to any other source of noise. So for example, if the world was vibrating, the vibration of the world will be coupled to these mirrors because these mirrors are hung from the ceiling. So they have to essentially create the world's best vibration isolation system to ensure that no matter what happens, the distance between these two mirrors does not change by more than 10 to the minus 18 meters. So it's a combination of optical interferometry and vibration isolation in order to measure these very, very small length changes. Are there any questions about this? Okay. So why can't LIGO go below 10 hertz?
I have a question, Surjeet.
Yes.
Do you think this LIGO type of instrument which we have today can be improved, or it has reached its limits of improvement? Or
improvement meaning in what sense, right? So I think LIGO can get better at more sensitivity. It is harder for them to go to lower frequencies. They may be able to do it, but so this is exactly the problem we're going to talk about right now, because what you see is that, no matter, one can build a vibration isolation system, right? But like how much isolation you're able to provide depends a lot on how much the intrinsic noise is. So if there's a lot of noise, it becomes more and more difficult for you to be decoupled from it. So what we know about planet Earth is that if you look at just the seismic activity on the ground, which you can just measure with a seismometer, you basically see that at frequencies below 10 hertz, it shoots up very rapidly. It goes as a frequency to the 4th power, right? So essentially between 10 hertz and 1 hertz, the noise has shot up by 10 to the 4th. So you have to essentially build a 10,000 times better vibration isolation in order to even get to the same frequency you were trying to look for, same sensitivity you're shooting for earlier. So LIGO, I think, more reasonably can become more sensitive. They can be sensitive to lower amplitudes of gravity waves at their current frequency band. I think that is their plan of what they're trying to do. They may even be able to push their sensitivity from like 40 hertz to 10 hertz, but I think below 10 hertz would be very difficult for them.
See. Okay. Thank you. Thank you.
Sure. All right, so that's the problem, right? We've got to confront the large seismic activity below 10 hertz. So here is the idea, okay? This is what we want to propose. This is an experiment called MAGIS. Suppose you could do the following, right? I want to build the world's best vibration isolation system. And here's what I'm going to do. I'm going to take the two mirrors of LIGO, okay? And then I'm going to drop them. As they're falling, I'm going to measure the distance between them, okay? Now notice that these two mirrors are just simply falling. As they're falling, if a gravitational wave goes by, the distance between them will continue modulating. So I can use all my very precise instruments to measure the distance between them. But of course, the system is now completely vibration isolated, because as these things are falling, since they are no longer held to the ceiling, if the world vibrates, the vibration is not directly felt by the mirror, right? So if I could do this, I've basically solved LIGO's problem. I've created the world's best vibration isolation system. Of course, this sounds nuts because, the mirrors of LIGO are 40 kilograms of sapphire. So if you keep dropping them, you may break it once in a while and people will get very angry at you because that's a very expensive thing to do. So you cannot drop 40 kilogram sapphire mirrors, right? That's why LIGO doesn't do this brilliant thing. So the question really becomes, is it possible for us to drop something much cheaper, yet something that is extremely precise? So if you could do this, you have solved the problem. And I'm going to claim you can just drop cold clouds of atoms and measure the distance between them. So that's what this technology of atom interferometry is really about. So here is the idea. Okay, I'll tell you how an atom interferometer works shortly, but let me just give you the cartoon first. Here's what we're going to do. Okay, we're going to find a kilometer-long vertical mine shaft. Okay, so there's some mine that you go in the world. You find these long mine shafts there, and they're about a kilometer long. And what you're going to do is you're going to drop a cold cloud of atoms at the top, something like 10 to the 8 atoms at the top of this mine shaft, and drop another 10 to the 8 atoms at the bottom of the mine shaft. Okay, and these atoms are just in free fall. They're just simply falling. As these atoms are falling, I'm going to use a technology called atom interferometry to measure the distance between these two cold atom clouds. A gravitational wave going by will cause the distance between these cold atom clouds to modulate, because gravitation is universal. It doesn't care whether there's a mirror or an atom. It will cause the distance between them to modulate. But obviously, since these are just freely falling atoms, if the world is vibrating, there is no direct seismic noise on the atoms, right? This is the equivalent of taking the mirrors of LIGO, dropping them, and measuring the distance between them as they're falling. So here comes the question. How can I do this measurement, right? Remember, I need to measure distances down to 10 to the minus 18 meters, or equivalently time I have to measure to 10 to the minus 23 seconds. How do I do this? And that is through this technology of what is called an atom interferometer. And let me quickly tell you what that actually is. So here is a space-time diagram of an atom. Okay, so this is space in the x-axis and time in the y-axis. So here's what you do. At time t equal to 0, you take an atom that is in some eigenstate of momentum. Okay, so it's a momentum state p. That's what it's in. At time t equal to 0, okay, so you've simply taken an atom now that is moving with some velocity. That's all that's going on, right? At time t equal to 0, by some magic, which I will describe later, called a beam splitter. Okay, so here is a magical thing that I've invoked by something called a beam splitter. I will place the atom in a quantum mechanical superposition of momentum state p and momentum state p plus k. That means all you did quantum mechanically is that you took momentum p, and that guy is still going and doing its thing, but half of it is going in p, the other half is going with momentum p plus k. So basically, you have kicked a part of the atom. Remember, this is quantum mechanics, right? So it's a single atom. The single atom has now gotten two different momenta, basically. And then at time t, what you do is something called a mirror. I'll again tell you what that actually is. And what this mirror does is that it takes the arm that used to move with momentum p and makes it move with p plus k. So this guy becomes p plus k, while the arm that was moving with p plus k now moves with p. So this guy becomes that. And of course, the system is continually evolving. So there is going to be a differential phase between these two arms of the atom. And what you do, you want to measure the differential phase. So to measure the differential phase at time 2t, you apply another beam splitter. And that beam splitter takes a state p plus k to the linear combination p plus k minus p. And by unitarity, it takes p to the linear combination p plus k. Okay. So let us now look at the final state of the quantum mechanical state of the atom at the end of this entire process. The final state basically becomes 1/2 1 plus e to the I delta phi p, 1 minus e to the I delta phi p plus k. So this is just quantum mechanics, right? I haven't told you how these technologies actually work. I'm just telling you, if that could be done, this is the quantum mechanical state of the atom at the end of the day. So how do I measure the phase delta phi? What I can now do is simply count the number of atoms with momentum p and the number of atoms with momentum p plus k. And the number of atoms with momentum p is simply given by the probability of finding this atom in momentum p, which then is cosine squared delta phi, and the probability in state p plus k is sine squared delta phi. So by basically measuring the number of atoms in momentum p versus p plus k, I can measure the phase delta phi. That's basically how this whole thing works. Are there any questions about this?
Yeah, but Surjeet, I have it's probably a dumb question. So in the picture that you have drawn, it seems like at a fixed time, the atom is localized in R. So how can it be in a momentum eigenstate?
Oh, so in reality, these are more like Gaussian states. So think about it that way, right? So it's not exactly a momentum eigenstate. I spoke too quickly in that sense, but they're sort of like, it's kind of a Gaussian wave packet, basically.
Okay, I see.
Yeah. It's more the fact that if I look at the distribution in momenta, p plus k and p will have very little overlap.
So I should think that there is a sum over p here. I mean, there's something that you suppress.
Yeah. There is some wave packet, and there's some wave packet on p plus k. And the key point is that as long as the overlap between them is very small, I can effectively think of it like this.
Okay, thanks.
Sure. All right. So I have to now tell you the magic, right? How did I do all of these beam splitter, mirror, right? So the key point is that the beam splitter and the mirror and all these kinds of things, what they are really doing is they are taking a quantum mechanical system that is initially in some momentum eigenstate or something or p and putting it in some linear combination p and p plus k, things of that kind, right? So here is the main idea. There are certain elements in the world, okay, strontium, mercury, some of these guys, which are, I forget the chemistry name for this. I think they're called alkali or something like that. So these are guys that are the second part of the periodic table, okay? It's after sodium, whatever comes after sodium. So these guys have this fact that they have a ground state and they have a first excited state. The first excited state is split from the ground state by 1 electron volt. So that's a pretty large splitting, okay? And typically atomic states live for very short times, like sub-nanosecond. But it turns out that these states, the time to decay from this state to the ground state, if you excite it, is very long. It's like 1,000 seconds because these are highly forbidden transitions, essentially. So because of that, what these things actually end up doing is that if you take this particular ground state, the atom is in this ground state, you then hit it with the laser light with frequency omega-1, and that actually will drive you from the ground state to the first excited state. Okay, so this is the main idea. And I don't know if I have a specific. Okay, I don't think I did that specific thing. So let's think about this in quantum mechanical terms. What's actually happening, right? So if I take a ground state of this kind and I expose it to some laser light, I've coupled this ground state to the excited state. So what will actually happen now is that this system will undergo Rabi oscillations, right? So Rabi oscillation meaning that I initially take my system, all of it is in the ground state. I turn on this perturbation, it will now start getting mixed up with the second excited state. And that basically means that initially I start with the state all in P. If I wait for, let's say, a quarter of the Rabi period, a quarter of the Rabi period, I will essentially have half the atoms in the ground state, the other half will be in the first excited state. If I wait for a half of the Rabi period, all the atoms that used to be in state 1 will now be in state 2, so on and so forth. So essentially, I'm just going to use Rabi oscillations, and I'm going to control for how long the atoms are exposed to the light in order to basically achieve this beam splitter in the mirror. So let me switch back over here and tell you how it actually works. So if I want to do the first beam splitter, right, I initially had the atom, all of it was in momentum state P. I turn on this laser. There is now a Rabi frequency in the problem. I wait for half the Rabi period, a quarter of the Rabi period. That basically would mean that quantum mechanically, the system will now automatically evolve to this state. If I want to do the mirror pulse, I take this particular quantum state, I wait, I turn on the laser, I now wait for half the Rabi period. If I wait for half the Rabi period, everything that is in P will go to P plus K, and everything that's in P plus K will go to P. So by simply turning on the laser light and waiting for the appropriate Rabi period, I can control whether I am turning on the beam splitter or the mirror pulse. So that is just a basic quantum mechanical idea of what's actually going on. Any questions about this? All right, there's a question.
Yeah, what suppresses the decay rate? Is it because of alpha fine or M electron by M proton?
It's actually various angular momentum factors. So these are like forbidden by one of those selection rules. So it makes it a highly forbidden transition essentially. So there are basically large powers of alpha that appear in there. So here's the key question. Okay, the key question is basically, if I think about this particular setup, let me move back to this thing. Sorry. You notice that if I'm looking at the signal in this experiment, the signal in this experiment will depend upon how much momentum can be given to the two different arms, right? Because of course, in the limit that the two arms have exactly the same momentum, the quantum state is not split at all. So the signal will be zero. So essentially the idea is, how much momentum can I give in the system? How split can the system really be? How do I accomplish large momentum transfer? That's the fancy word for it. So here is how actually this technology we came up with. How do we achieve large momentum transfer in these kinds of systems? So here is what you do, right? You have your atom. Initially, it's in the ground state with momentum P. You turn on this laser light. You drive the transition from momentum state P to momentum state P plus K. So you've done one excitation. Okay, so you can think about that as the coherent absorption of this radiation from the ground state to the first excited state. So to do this, your laser was effectively from the left, and then what's happening is that the laser is coming in from the left, which means the atom absorbs that light and gets a kick to the right because the laser light is moving to the right, obviously. Now you can do the following. From the left, you can send another laser that is moving to the left side like this, right? This laser light. But now what's happening is that instead of it getting absorbed anymore, because this is a coherent quantum mechanical process, this laser light will drive this transition via stimulated emission. Okay, so when you are in the ground state, this laser drove you into absorption, which is what gave you a kick to the right over here. When you drive this laser light is actually going to the left in this side, but the atom is not getting absorbed because this laser light is not tuned to any absorption line over here. It is simply tuned to the same frequency, which means this quantum mechanical state has no option but to undergo stimulated emission. So if it undergoes stimulated emission, it will of course emit laser light going to the left on this side, which means the atom itself will get a kick to the right through sort of conservation of momentum. So effectively what you have done is that anytime you drive this transition, this set of transitions, right? Let's look at what's happening. I kick initially to the right via absorption, then I undergo stimulated emission, which also kicks me to the right. So effectively at the end of this process, I have kicked the atom twice to the right, but I've now come back to my original ground state, 1, except I've now got a momentum kick 2K. And now I drive it again, right? So now kick it, this is now in the same initial ground state, but his momentum is P plus 2K. You drive this guy, he goes to P plus 3K. You then hit this guy from the left again. So that basically takes it back to, well, I think I messed up my numbers here. There should be 3K to going to 4K. I should fix my slide. Okay. So effectively, you just keep driving this transition repeatedly. As you keep driving this transition repeatedly, you end up transferring a lot more momentum to the atom than you naively was possible with a single kick. That's kind of the idea. Just kick the atoms from the left and the right. So here's a space-time diagram for how we're going to do this. So you take your atom, it is being dropped. You hit it with a laser light from this side. This laser kicks it. At that point, you know, essentially half the atom, let's say, has picked up some momentum. And then when this laser light reaches on the other side, you send another laser beam to the opposite direction, which then means that this atom will undergo stimulated emission, which of course gives it a kick back in the right, but now you're back in the same ground state. Okay, just that you're now moving faster, at which point you now hit it again on this side. which now means that you get excited, you got a kick to the right, and then you keep doing it. So essentially, every time these two photons go back and forth, we usually call this bing bang. That's our technical term for it. Every time you do a bing and a bang, you've basically gotten this kick. Okay, so that's what you keep doing. It's a large momentum optical clock technology. And what the system is fundamentally measuring is the fact that anytime your atom is in this linear combination of ground state plus excited state, there will be a relative phase between them, right? Because there's an energy shift between the ground state and the excited state of order 1 electron volt, and because there's a difference in energy, there will be a difference in the phase between the ground state and the excited state, and you can use that effectively as a way to measure time, right? That is a key idea, because once there's an energy shift, this phase shift becomes a measurement of the amount of time the atom is actually spending between the ground state and the excited state. That's basically what's happening. Any questions about this? All right. So here is the top level idea of what we are trying to do, right? A lot of that discussion earlier was just technology. Here is sort of the fundamental physics way of looking at it. What are we trying to do? Think about the following thought experiment. Suppose I take two clocks at A and B, okay? And what I'm going to do is that from clock A, I'm going to be sending light pulses at times T, 2T, 3T. That's all I'm going to be doing. I'm sending light at a fixed time, T, 2T, 3T, so on and so forth. And I'm going to sit at B and record the time of arrival of these pulses. That's all I'm doing. That's my fundamental idea, right? So if nothing was going on between A and B, by nothing, I mean the distance between them was constant. Even if I send light at time T, 2T, 3T, so on and so forth, and the distance between these two guys is L, the time at which the light will be received here will be T plus L, 2T plus L, 3T plus L, so on and so forth. While if there's a gravitational wave going by, the distance between A and B will modulate by some amount epsilon, which means if I send light at time T, 2T, 3T, so on and so forth, when I'm receiving the light over here, the light will be received at time T plus L plus epsilon, 2T plus L minus epsilon, so on and so forth, right? So when there's a gravitational wave, the time of arrival here will modulate, as opposed to when there is no gravitational wave, the time of arrival is constant. The time between them is constant. So that's the key idea of what we're trying to do. So here is how this gravitational wave instrument is actually going to work. We are going to take this, as we said, this kilometer long mine shaft, go to the top and go to the bottom, drop these cold atoms. As these atoms are falling down, we're going to hit them by this counter-propagating laser light. So you can think of this, let's say, as being at the bottom of the mine shaft over here, and this is the top of the mine shaft. So we have one atom cloud very close to the bottom, another atom cloud very close to the top. We start the whole process, for example, by sending light from the bottom of the mine shaft. It hits the first atom cloud on its way. It then goes and hits the second atom cloud. And then we kind of do this bing bang process many, many times in order to measure cause all these atomic transitions. So how does a gravitational wave show up in this particular experiment? What's happening is the fact, right, essentially that if you think about it, the system is keeping time anytime the atom is in a superposition between blue and red. Okay, so think about the gravitational wave in the following way, or any kind of timekeeping in the following way, right? In the beginning, in this part of the instrument, the amount of time the atom spends in the excited state over here is extremely small, right? As this figure clearly shows, which means no time is really being measured on this side of the instrument. While over here, because of the superposition, I'm effectively being able to measure the amount of time the atom is spending in the excited state here. While as I go to the top, that is completely flipped, right? I'm spending more time over here than I am on this side. So effectively what I'm doing is I'm basically comparing how much time is the atom spending in the excited state in the first part of the experiment versus the second part of the experiment. So if a gravitational wave goes by and it causes the distance between these atom clouds to change, for example, I may spend more time in the beginning over here than I will over here. And that's exactly what shows up in my experiment. Unlike a laser interferometer, which requires 2 arms to operate. And we said the reason for that is basically because laser phase noise was a reason, right? The laser is noisy, and I needed 2 arms to basically cancel the laser phase noise. In this particular experiment, I don't need 2 arms because whatever noise is happening in this laser is going to be common to both these interferometers. So this laser noise is going in here, it'll affect this atom interferometer in the same way that it'll affect this atom interferometer because it's the same laser pulse that goes through both these guys. Which means when you subtract the phase in one experiment versus the other experiment, the laser noise will be completely canceled. So one does not require 2 arms of an interferometer. One can just simply use a single arm interferometer. Okay, so essentially this really is realizes this theoretical idea that we talked about in the previous slide, which is that I'm just simply comparing 2 distant atomic clocks. Each of these things can be thought of as a clock in the presence of a gravitational wave. And that's really all that's actually happening here in this instrument. So let me tell you the terrestrial configuration. We've already talked about it a little bit. So this is kind of what we want to do. We want to find a kilometer-long baseline. We're going to take 2 10-meter atom interferometers. That is, the atoms will drop about 10 meters, essentially, at either ends of a mine shaft. And then we put these common lasers at the top and the bottom. And the signal in this experiment, of course, scales with a kilometer separation between these 2 things because HL, that's a distance that's actually modulating. And in 10 meters, the atom will essentially take about 1 second on the ground to fall, 1/2 GT squared. And so we'll be maximally sensitive to gravitational waves in the frequency band of around 1 hertz on the Earth. That's basically what the plan is. And, you know, it took us a long time to get this off the ground due to all kinds of politics. But things are actually off the ground now. So what's going on is basically in Fermilab here in the United States, as well as at Stanford, there's this experiment called MAGES. It's being funded reasonably well. The Moore Foundation gave us about $10 million. And the DOE, the Department of Energy, has put in another 4 to 5 million. So we're actually building a proof of concept apparatus, which will show a lot of this technology on the ground. That's kind of what we're funded to do. But there are now a number of other people who have also signed up. So there is something going on in France called MIGA, that is in the French Alps, and also a variety of other experiments in Europe as well as the UK. And more recently, the Chinese have joined in through an instrument called Zyga. So here is kind of what some of the technology is looking at right now. We talked about some of this earlier in the context of dark matter as well. So this is what's happening at Stanford right now. They're going to prove a variety of these technologies. They're essentially dropping co-located clouds of rubidium-85 and 87, and they're using the same idea of atom interferometry to test if one of them is falling faster than the other. This is Galileo's experiment, right? So that is their goal. This is what they want to do. And what they've actually demonstrated technologically is that they're able to measure phases of atoms down to something like 10 to the minus 4 radians. And this thing that we talked about, right? How much momentum transfer can we actually give to the atom? Like how many times can you drive this optical transition that we talked about, this business of large momentum transfer beam splitters? They've been able to do that to about 141 now, okay? And they've got that cooling down to picokelvin temperatures and even a little bit of what is called spin squeezing in order to improve these phase sensitivities a little bit. So the job of the Fermilab apparatus is to put all of these things down in a 100-meter apparatus. So the Stanford experiment is about 10 meters in size. Fermilab, we're going to scale this up to 100 meters and show that all these things actually work. And the goal is to improve these numbers by factors of 10 in each case. One can also do the same thing in space. One can essentially think about putting 2 satellites in orbit and separate them by something like 1,000 kilometers. Okay. And then basically you do the same idea. You have atom clouds in one spacecraft, atom clouds in the other spacecraft. You then send these laser light from one to the other and measure the distance between them as accurately as you can. And the main limit on how much separation one can actually do is that if you do something very dumb, where you just have a big mirror and you send the laser from one side to the other, you don't want to lose too much laser power as you go from one side to the other. That basically says you can separate these 2 instruments by about 1,000 kilometers. Although larger distances are possible, this is the simplest thing one can actually do. So I won't go into too much detail about this, but basic idea is that if all of this works, in terms of the technology working as we hope it does, we will be able to probe gravitational waves from about 0.1 hertz to about 10 hertz, let us say, with a sensitivity of around 10 to the minus 21. That's basically what we're hoping to get. which will park us really between what LISA wants to do and what LIGO has already done. So we're hoping to cover this mid-range frequency band with these instruments. So are there any questions about this?
Yeah. How do you
measure the phases of the atomic states? Yeah, so this is what we talked about earlier, in the sense that essentially you will be counting the number of atoms that are in the ground state versus the excited state. So let me actually go back to that part of the discussion all the way here. Oh, actually, let me go to atom interferometry here. Sorry. Okay, let me put it back. Okay, so here's what you're doing, right? You basically say, let's say P is one ground state, and P plus K is the other, is the excited state. So if you go through the mathematics of what's going on here, you notice that these two guys have two separate phases. So when you perform your final beam splitter, this becomes the overall final state of the system, right? So there is the phase that you showed up here appears once you do the final beam splitter as 1 plus e to the I delta phi in ground state, 1 minus e to the I delta phi in the first excited state. So all you're going to be now doing at the very end is you take a picture. You count how many atoms have momentum P, how many atoms have momentum P plus K. When you do that counting, because of the quantum mechanical thing that's going on here, the number of atoms in state P is proportional to cos squared, and the number of atoms in state P plus K is proportional to sine squared. So you're just simply taking a picture of the number of atoms in momentum P versus P plus K, and that will tell you what the phase is. Okay, great. So let me move on to the next part of the talk. So majors, as we talked about, is actually happening, right? In the sense that there is technology development going on, and I'm hopeful that things will actually take off. So now let me talk about very new ideas, things that don't have any money for them attached to them, and that the papers are just being written. So we're going to talk about asteroid ranging between a microhertz frequency and 0.1 millihertz. So let me go back to my original gravitational wave spectrum. We talked about mid-band detectors. That is basically where sitting between LIGO and LISA. And now we're asking, how can I go to lower frequencies, right? I want to cover as much of this band as possible. And the key thing we realize is that as I go to higher and higher frequency, I require more and more precision. As I go to lower and lower frequency, I require more and more stability, because precision is not the main difficulty here, it's more stability. So how do we combat this? So before we go to microhertz frequencies, let's talk about LISA briefly. Okay, so why is LISA what it is? What is LISA trying to do? LISA is trying to do the following thing. LISA has got 3 different satellites. Inside those satellites, they have what is called a proof mass or a test mass, and they're trying to measure the distance between these test masses very accurately using a laser interferometer. So the idea is that if the test masses are not moving due to anything else other than just gravity, right? If a gravitational wave goes by, the distance between those test masses will change, and LISA is going to measure those test mass distances very accurately with a laser interferometer. That's the basic idea. Now, they're in space. So obviously, when the world shakes locally here, the test masses, we're very far from the Earth, so those things don't matter. So then you should ask, why can't LISA go to arbitrary low frequencies? Because they're in space. There's no seismic activity on space, which is what was blocking LIGO on the ground. But the key point is that even though you're in space, this test mass that LISA actually has is housed in a satellite, right? The satellite has got lasers, all kinds of things. So even though you're in space, this satellite will still get wobbled and wiggled by all kinds of things. The solar intensity on the satellite will fluctuate. There is charged particles going in. They'll charge the proof mass. The satellite also has outgassing, right? There's some gas in the satellite which will leave. So all of this will actually cause the position of the satellite to fluctuate simply due to all these kinds of noise sources. And as the position of the satellite fluctuates, it will gravitationally couple to the proof mass. So essentially think of this the following way. There is this satellite around you, which has got all kinds of mass, it's got lasers, all this kind of stuff. Inside that, you have a little test mass. This test mass is not attached to the satellite because the satellite itself wiggles too much. But what's going to happen is that as the satellite wiggles, no matter what you do, it will gravitationally act on that test mass. And at some point that becomes too big because you're trying to measure very, very small distances. So the ability to have a satellite wiggle without that wiggle causing this test mass also to move is called the ability to fly a satellite in a drag-free manner. That is, you have a test mass in here that is completely uncoupled from the space environment, even though there's a satellite around it. So that's a technological thing. It's called flying drag-free. And flying drag-free is very hard, okay? So in fact, this is so hard that even to get to what Lisa wanted to do, nobody in the world really believed that Lisa could do it. So Lisa had to fly a separate instrument called the Lisa Pathfinder to prove that they could actually do this. And Lisa Pathfinder worked really well. So Lisa Pathfinder showed that at Lisa frequencies, which are basically millihertz to 10 millihertz in that frequency band. So this is actual data, right? This is their actual noise that they discovered, that they showed. So Lisa basically showed that at Lisa frequencies, they were able to, in fact, fly a satellite and have a test mass that was sufficiently vibrationally isolated from the space environment at their frequency band. But notice, once again, that at low frequencies, the noise keeps shooting up, right? So at low frequencies, so as you go 10 to the minus 5 hertz, 10 to the minus 6 hertz or so, this noise becomes larger and larger and larger, right? So while Lisa Pathfinder achieved what it wanted to do for Lisa, you can't quite use the same technology at low frequencies because the noise keeps going up. Now, of course, it's possible that Lisa technology will get better and they're able to go to low frequencies. I'm not ruling that out. It's certainly possible, but I'm just asking the question, can you do something a little bit different? So here is the dumb idea, okay? I actually realized that this is the only equation that I've so far shown in these lectures. So I have to prove to you guys that I'm also a theoretical physicist. So I'll at least have this one equation shown up there. So what is the dumb thing you can do, right? So the problem that we were dealing with is the fact that, look, I have this satellite. The satellite is wiggling due to all kinds of noise coming and hitting it. At the end of the day, I'm trying to measure the distance between two objects. And that means what I really care about is the acceleration, not the force per se. So the dumbest way in which I can make the acceleration small is by increasing the mass of the object, right? Acceleration is F over m. And the larger the mass, if the force doesn't scale too badly, the acceleration will become smaller and smaller. But of course, the Lisa satellite is like 1,000 kilograms in mass. It's 1 ton or whatever. It's extremely expensive to put heavy things in space. So if I'm trying to put extremely heavy things in space, it's very, very expensive to launch it. So how am I going to launch heavier and heavier objects? Very expensive. Why don't we make use of natural objects instead of man-made satellites? So one thing I can think about using is a planet, right? A planet is enormous in mass. So obviously, if we look at the center of mass position of the Earth, right, the planet Earth, the center of mass position of the Earth is extremely stable. Okay, cosmic rays coming and hitting it, etc., are not going to change the center of mass position of the Earth very much, or that of a planet very much. On the other hand, I can't obviously use planet Earth because planet Earth, even though it has a very, very stable center of mass, its surface is very noisy, right? There's lots of seismic activity going on because the Earth has its heat of formation. There's atmospheric effects, all kinds of crazy stuff going on the Earth, which is why in the first place, I couldn't use planet Earth itself, the surface of planet Earth, as a good proof mass, which is why LIGO had to work so hard in order to suppress all of the noise on the surface of planet Earth. But what about an asteroid? Okay, a few kilometer scale rock. A few kilometer scale rock has the advantage that its mass is gigantic, which means its center of mass position should be pretty stable. At the same time, if you think about a rock, right, a 10-kilometer rock, it has basically lost all of its heat of formation because it's small enough that the heat has dissipated out. So you should actually expect that the surface of the asteroid does not have very much seismic activity. So in some sense, maybe an asteroid is the right object because it should have sufficiently small seismic activity. So its surface should be stable enough. Meanwhile, a center of mass position is also stable because it's big enough, right? It's somehow maybe the ideal object between a few thousand kilogram satellite and an enormous planet. So that's the idea. So the concept is, could we put two robotic craft on two different asteroids? Okay, so That's literally what I'm talking about. 2 different asteroids. And I'm going to send laser or radio waves, let's say from one asteroid to the other, and do ranging. So basically, I'm sending laser pulses, let us say, at time t, 2t, 3t, as we talked about, from one asteroid, and it is received at the other asteroid. And we're simply measuring the time of arrival between these pulses. A gravitational wave will cause the distance between these 2 things to modulate. And that is something you can then sit and measure using this thing over there. So that's the basic idea. How well do we have to do, right? So here we are going to make use of the fact that at low frequency, the precision I need is not as stringent. For LIGO, I'm looking at gravitational waves of around 10 to the minus 22, 10 to the minus 23. At these low frequencies, I'm looking at 10 to the minus 17, 10 to the minus 18, okay? So which means if I take these 2 guys and separate them by something like 1 astronomical unit, the distance separation between them only needs to be about 1 to 0.1 microns, considerably higher than the 10 to the minus 18 meters that LIGO was looking for. So all I'm really interested in asking is, can I actually measure the distance between 2 asteroids to 0.1 microns or 1 micron? And is the center of mass position and the surface of an asteroid stable enough to 0.1 micron to 1 micron? That's the question that I'm basically asking. So before we answer those questions, can we actually ask, is this even reasonable, right? Have we landed things on asteroids? Do we have good enough atomic clocks to actually do this kind of measurement that we're talking about? So first of all, it turns out that we've actually landed on asteroids. We've been going to asteroids for about 2 decades now, both NASA and the Japanese Space Agency. For a number of technical reasons, landing on asteroids is technically easier than landing on something like the Mars or on Mars or the moon. Basically, because if you think about it, right, you launch your rocket from the Earth, and as you go to Mars, one of the things you have to do is to slow down to land on Mars, because Mars, of course, has its own self-gravity. So you have to go and slow down. And that's, of course, quite complicated because you've lost your expensive rockets when you got out of planet Earth. And when you go to Mars, you don't really have another rocket to slow you down. So this is why anytime you look at any Mars landing mission, they have the last, whatever, half an hour of terror or whatever it is, where they have to slow down very, very nicely and gently to land on the surface of planet Mars. But if you think about an asteroid, the asteroid is small enough that it does not have a whole lot of self-gravity. And because it doesn't have a whole lot of self-gravity, what you can do is that you can launch yourself from planet Earth with the right velocity so that when you get on the asteroid, you pretty much are moving at the same velocity as the asteroid. So you can very gently slow down and land on it because you don't have a whole lot of force you're combating. So for this reason, landing on asteroids is technically easier in many ways. Secondly, the kind of atomic clocks you require, right? We don't need the fancy things you need for things like LIGO, since these are orders of magnitude less precise in terms of what we need to do. It turns out that the kind of atomic clocks you need for this mission already exist on the ground. Now, nobody has flown one in space, but there's a lot of interest to do that. But on the ground, this technology basically exists. So, at the sensible level, you're sort of like, well, how outlandish is this? These things don't seem too outlandish because we have landed on asteroids and we have good enough clocks on the ground. So now the main question is the physics still sensible? Is the asteroid surface and center of mass sufficiently stable to perform this kind of measurement? So there are a variety of noise sources that one can go look at. Things like the dominant ones basically turn out to be the fluctuations of solar intensity, solar cycling. People have studied a lot in terms of what kind of seismic activity there could be on an asteroid, largely because we've in fact landed seismometers on the moon. And the observation of seismic activity on the moon basically tells us that the main source of seismic activity are things like tidal activity and thermal cycling. So thermal cycling happens because the moon is looking at the day for some time, and then as it rotates, it switches to the night. And there's a huge variation in temperature, which actually causes thermal cracks and stuff like this. So the bottom line of all of this is that if you look at actual seismic activity on the moon, you could look at actual measurements. Those measurements say that the largest seismic things that you don't normally see are actually more in the nanometer scale, nanometer to 10 nanometer scale. So those things should be comparable on the asteroid as well. quite a bit smaller than 0.1 micron that we are actually interested in. Some kind of quakes happen on the moon due to tidal activity from the Earth, but asteroids are pretty far from any planet, and tidal strains are extremely sensitive to distance, it turns out. So the dominant source of noise that you see on the moon due to seismics should not really be a problem for us. So we've kind of gone through a variety of these noise sources, and basically what we see is that the dominant source of noise is essentially intensity fluctuations from the sun and solar wind fluctuations. So those effectively turn out to be the biggest source of noise. And if you have a few kilometer asteroid, they're basically small enough. That is the dominant things that we've actually found from our study of this. There is, in fact, another source of noise, which we will talk about shortly, which is very important at lower frequencies, which is coming from the fact that if you look at the solar system, there are lots of asteroids, right? So there are about 1 million asteroids or so in the main belt, and these asteroids will gravitationally act on other asteroids as well. So what I'm trying to do in this experiment is trying to measure the distance between two asteroids very accurately. So when you have 1 million asteroids going around, they will of course gravitationally act on them and cause the distance between the asteroids to fluctuate. And in fact, this was so important that we studied this separately, and we find that at low frequencies, at frequencies below microhertz, that rapidly shoots up, though above microhertz, it's small enough that it's not a problem. So the bottom line of all of this is that we've gone through all these dominant noise sources, and we actually believe that at frequencies above a microhertz, right, all these noise sources are small enough that is very reasonable that if you actually send, a sort of robotic craft on two different asteroids and measure the distance between them, you can actually use asteroids as natural test masses to see gravitational waves above a microhertz, essentially between, somewhat below the frequency band of LISA. Okay, so that is the main idea. Now, of course, nobody has actually gone in an asteroid itself and measured the actual seismic activity there. So before this measurement actually happens, what we are hoping to do now is motivate these guys who go to asteroids fairly regularly. We're hoping to convince them to land some seismometers on them and actually make in situ measurements of seismic activity. And if that seismic activity is observed to be small enough, as we expect it to be, we can then go ahead and launch a full-scale mission to actually see gravitational waves in this frequency band. So are there any questions about this? Okay. All right. So if there aren't any questions, let me move on to the next part of the talk. So this is actually just this thing that we're hoping to do here. We're going to hope to operate in microhertz and LISA essentially. So notice that I couldn't go to frequencies below microhertz. The reason why I couldn't go to frequencies below microhertz is because of the fact that of this enormous noise coming from the other asteroids in the solar system, right? These million asteroids going around, they will actually pull these asteroids by very large amounts at frequencies below a microhertz, roughly at the periods of these asteroids where they're going around. So what can one actually do to see gravity waves between 10 nanohertz and 1 microhertz? That's basically what we're talking about. So it's very hard to model this out, essentially because of the very large amount of noise, the large number of asteroids in this belt, right? So notice that this noise is true not just for measuring distance between two asteroids, it is true for any gravitational wave setup that is trying to measure the distance between two satellites or two test masses. So if I have two test masses, say two very fancy satellites that I'm placing inside the inner solar system, right? It doesn't matter whether the test masses are due to satellites or whether they're actually asteroids. No matter what it is, the distance between them will fluctuate because of the gravitational noise from these asteroids going around us. So the question really becomes, if I am trying to detect gravitational waves with a detector that is in the inner solar system, okay, what can I do? I cannot use two test masses. That's basically what we're actually seeing. I'll ignore this particular thing, right? So what can we actually do to see gravitational waves below microhertz using a detector in the inner solar system? So with this, you might already be a little bit confused, right? So what am I talking about? I basically said I cannot do anything in the inner solar system at frequencies below microhertz because of this large noise from asteroids. But I said in the very beginning of my slides, there is already an experiment underway called nanograv. Okay, and there's in fact lots of reasons now to think that perhaps they've already seen gravitational waves at low frequencies. How are these guys able to see gravitational waves at a frequency of a nanohertz? And that's an Earth-based experiment. How are they able to do it? Well, what is nanograv actually doing, right? What they're actually doing is that they're not looking at objects in the solar system. They're looking at very distant objects. They're looking at pulsars, right? So the way nanograv works is that they're actually looking at pulsars. These pulsars are emitting they're emitting radio waves at very significant constant periods, and they're sitting on the Earth and measuring the time of arrival of these pulsars, from pulsars, regularly. And the distance between us and the pulsar is modulated by a gravitational wave, and it is that modulation they're actually sensing. So why are they insensitive to these kinds of noise sources? That is basically because they're looking at an object that is so far away that the intrinsic distance change caused by the gravitational wave is considerably bigger than what you're able to do. So if you take two objects and separate them by a distance L, the larger that distance is, the more the distance separation caused by the gravitational wave is. In fact, effectively, it can be as large as the wavelength of the gravitational wave. That's how large it can be. So at nanohertz frequencies, it turns out that the signal from the gravity wave is enormously big, much bigger, because of the fact that the distance between the Earth and the test mass, in this case the pulsar, is very, very large. So that is basically how they're able to drastically increase their signal without increasing their local noise. That's how the pulsar timing arrays work. And they're great. As I said, there is rumors that they've actually detected gravitational waves at these low frequencies. So while they're terrific, you notice that they're very, very good at a nanohertz frequency. As you go to higher and higher frequencies, their sensitivity drops off. So the question really becomes, what can you do, okay, between the sensitivity of these pulsar timing arrays and, let's say, microhertz frequencies, where one might be able to do some kind of local test mass detector, whether that is through an asteroid like we talked about, or through some kind of satellite experiment. What can you actually do, right? So as we said, pulsar timing arrays, they detect gravitational waves basically because they're looking at time of arrival of pulses from distant pulsars, right? And that only works because pulsars are known to be stable clocks. So one can ask, what are other stable aspects of distant astrophysical objects? What else can I actually make use of? One other thing you might try to make use of is the center of mass position of stars. Because as you said, the center of mass position of a star should be very, very stable. But of course, I can't really measure the center of mass position of a star that well from the Earth, right? I'm not going to send a probe from the Earth to the star and how it bounce back and come back to me. I can't do that. So the only way I can actually measure the center of mass position of a distant star is by some kind of angle measurement. An inferred angle between two stars can be used as a way to measure the center of mass position. And that brings us to the topic of what is called astrometry, where we basically look at two different stars and we measure the angle between them very accurately with a detector that is we fly in the solar system. That's basically what we want to do. So how does the gravitational wave show up? Well, here is this star sending light to us. Here is this star sending light to us. As a gravitational wave goes by, the light pulses will be changed ever so slightly as they're arriving. That means the angle between these things will change ever so slightly. And in fact, you can show that the angle between them will change by an amount h, where h is the strain of the gravitational wave. So the challenge here is that I have to be able to measure the angle between these two guys with a precision of around 10 to the minus 15 to 10 to the minus 16. And that is essentially what we have to do. And the question now basically becomes one of stability. Is it possible that there are these astrophysical sources that are sufficiently stable at the level of whose angles are stable to the level of 10 to the minus 15 to 10 to the minus 16? How well can we really do that? That's the question. So one of the key issues that shows up in this particular story is that since I am actually measuring the position of these stars, not by directly measuring the center of mass, but by measuring its angle, I'm actually sensitive not to the geometric center of mass of the object. I'm sensitive to the photometric center, right? I'm basically looking at the light coming from this object, and I'm essentially measuring the angle between the center of light between one star and the center of light of the other star. What can mess this up? One thing that can mess this up is that stars have things called star spots in them, right? The sun has sunspots. And when there's a star spot, that will obviously change what the photometric center is. Even if the physical center is not changing, the photometric center will change because all I'm sensitive to is the total brightness of the object. So if the star, for example, had a star spot appear and disappear, it will in fact change the photometric center, even if the physical center is not changing. How bad can that be? Well, here is a simple calculation. If you assume there's a star spot of size R, which is order 1 different in intensity, you can basically realize that the angle change basically goes as this intensity contrast times the physical size of the star divided by the distance between the Earth and the star. So what you learn is that for a fixed contrast, okay, in the star spot, how dark the star spot is compared to the ambient light, you notice that smaller the star, the smaller the angular change. The further the star from us, the smaller the angular change. So if you want to suppress this noise, it makes sense to look at a smaller star and a star that is further away. So a natural thing to think about in this context is that since I'm now more interested in smaller stars, maybe I want to think about white dwarfs, right? White dwarfs are only 10,000 kilometers in size, as opposed to a main sequence star that is 600,000 kilometers in size. So maybe I want to look at a smaller star, essentially. So it turns out that there are observational evidence to back this up, that if you look at this question, I'm basically saying, look, I want to see gravitational waves, and I want the photometric center to be stable to 1 part in 10 to the 15 or 1 part in 10 to the 16. You can basically realize that if you have a star that is at something like kiloparsec distance effectively, then you only require the intensity stability to be at the level of 1 part in 10 to the 4. That's a simple calculation you can do. And we actually have measurements of white dwarfs whose intensities are known to be stable to 1 part in 10 to the 4. There has been measurements made to what is called the Kepler instrument, and they anchor what are called the Landholt standards in astronomy. They basically know that these guys' intensities are stable enough. So effectively, you look at white dwarfs that are at a kiloparsec distance. We know that their angular positions should be stable to 1 part in 10 to the 16 based upon intensity measurements that we've already been able to make. The second thing that's also very interesting for a white dwarf is the fact that I want the center of mass position to also be stable to this level. So one thing that can actually cause a white dwarf center of mass to wiggle, okay, is the presence of planets, right? A planet that is nearby will cause the star to wobble back and forth. But the key thing is that if you basically are interested in looking at frequencies above 10 nanohertz, the planet has to be within 1 astronomical unit in order to cause a frequency fluctuation at that frequency, right? Because of Kepler's law. Now, notice that when you're thinking about a white dwarf, before the star becomes a white dwarf, it goes through a red giant phase. And during the red giant phase, the star actually enormously increases in size. It actually becomes 1 astronomical unit in size, which essentially means that by the time you've gotten to a white dwarf, the red giant phase will expand out and eat up whatever rock or planet that is out there within 1 AU. So you're basically guaranteed that out to a distance of 1 AU or above a frequency of 10 nanohertz, there are no planets, there are no asteroids or rocks that are going to be close enough to cause problems to you, right? So effectively, if you're able to do astrometry of white dwarfs, so instead of looking at distance between 2 random stars, let us look at distance between 2 white dwarfs. If you, the angle between 2 white dwarfs. If you're able to do that, you'll actually have a nice case to measuring gravitational waves, okay? So what does it require technologically to do this? Essentially, you want to build an instrument. I'm going over this very quickly. You're able to build an instrument that is able to detect light at 120 nanometers or 1200 angstrom. And you are basically building an interferometer in space where you take 2 mirrors, separate them by about 1 kilometer or so, and then you're able to do some kind of optical interferometry between them. Roughly, you have the ability to detect gravitational waves with a strain of around 10 to the minus 16. Okay, and instruments of this kind were proposed, and a lot of technology development happened. There's lots of NASA politics. I don't know all the details about this, So there was an instrument called the Stellar Imager that was proposed back in the day, and it has exactly the same kind of features. They're thinking about separating two things by about 1 kilometer with a ability to measure light at this frequency of around 120 nanometers. So if that kind of instrument is built, okay, it will be able to detect gravitational waves above 10 nanohertz. So that's pretty much all I want to say. People thought these instruments were possible, that you could technologically build them. They're of course very expensive, at which point you get into all kinds of politics, which I can't really speak to. All I can say is that if such an instrument is built, which people thought one could do 20 years ago, you have an extra thing you could do now, which is that you can go and look at white dwarfs as opposed to the main sequence stars they wanted to look at back in the day. But by looking at white dwarfs, you can actually see gravitational waves. So with that, let me stop. Gravitational wave science is here to stay. It will clearly be a very, very important part of humanity's exploration of the skies as it moves forward. And what we've talked about is that there are very interesting technological possibilities to detect gravitational waves over a wide range of frequencies. So with that, let me stop and ask and see if there are any questions.
Thanks very much, Surjeet, for 3 very nice lectures, illuminating lectures. So we have a few minutes for questions. Yeah, Spenta, please go ahead.
Hi, Surjeet, I wanted to ask a question which is a little bit different from the stuff that you have been discussing about the detection of gravitational waves. Is there any, is there any idea that you are exploring to measure the quantum nature of gravity? That is, the noise of the intrinsic noise of the gravitational field, maybe, which was born, before the recombination. Yeah.
So actually, not only do I have an idea, I have an experiment going to do it. Okay. So it turns out that so what you're trying to get to is, you want to ask, is the gravitational field somehow classical, or is it really a quantum field?
Yes, yes.
One way to detect that is by this quantum noise, but that's very hard to do. Okay. A much simpler and a way more effective way of doing it is through the following experiment. Imagine that you measure. So this is literally what I'm doing right now with some friends. Imagine you take a spin. Okay, spin, let's say, is in spin along. You take a spin that's along the x direction. You measure it along spin z, along z. That means it's 50% probability you get spin up along z, 50% probability you get spin down. Okay. Now, the only sensible way of understanding quantum mechanics, in my opinion, is the many worlds version of the story, which means the wave function of the universe now is half of it is in spin up, the other half is in spin down. What you now do is, depending upon the outcome, okay, of this measurement, you can do the following. You can either build you take your accelerometer, okay, take an accelerometer, and depending upon the outcome of your spin measurement, you bring a mass close to the accelerometer. So let's say you got spin up, you bring a test mass close to an accelerometer. You get spin down, you take the test mass far from the accelerometer. And what you can now ask is basically, is the accelerometer responding to the test mass that you brought next to it? Or is it responding to the expectation value of the test mass? Okay, so if gravity was a classical theory, which is what you're trying to ask. So if gravity was a classical theory, you would be responding to the expectation value of the test mass. As opposed to, if it's a quantum theory, you'd be responding to where the test mass actually is. So I encourage you to look at this paper that I recently wrote. It's called, in fact, we have what we call a nonlinear modification of quantum mechanics, but it actually has answer to the precise question you're actually asking, a version of it. And it is a much better way of, and in fact, a very doable way of testing this question, as opposed to what people like Wilczek have been proposing. And in fact, we have an experiment going. In fact, this majors experiment I talked about, one of the things it will actually do is test this as well.
Thank you. That's fascinating. Thanks.
Okay. Any other questions? I guess people are tired after 2 long weeks of lectures.
Yeah.
Yes.
How to overcome, let's see. Which interferometer? Are you talking about like the atom interferometer or the interferometer for asteroids? Which one are you talking about? Oh, in LIGO. Oh, so in LIGO, what they actually do, right, is basically that when the laser shakes, the shaking of the laser is going to be common, because essentially all that means is that the laser shakes, the laser light that is coming out is getting messed up. But the same light is being sent through both of their instruments, through both the arms. So as long as the mirrors are extremely vibration isolated, which is what they work very, very hard to do, all the noise in the laser will be common. So when they do the subtraction of the laser noise along the 2 arms, anything that has to do with the laser gets completely canceled. But the mirrors of LIGO have to be extremely vibration isolated. Using the most sophisticated technology, if we will be able to measure the quantum fluctuation in the vacuum. Well, I think the measurement of the quantum fluctuation in the vacuum is extremely hard to do. Okay. I don't know of any sensible approach to do that. You can think of it the following way, right? There are some people who have some of these proposals, but they're not, they violate effective field theory. So if you think about it, right, essentially when you have some quantum fluctuation, whatever is going on, in a Lorentz invariant theory, right, all you're doing at the end of the day is computing a propagator. So in a Lorentz invariant theory, if you're going to compute a propagator, you have some momentum k. What can you write down? The only terms you can write down are terms of the form k squared, so on and so forth. Right? You can't just put down terms linear in k. You can't put down terms that are square root in k. Those don't make any sense when you're computing those things, which automatically means that once it's a k squared that's happening in your propagator, it'll be suppressed by m-Planck squared, just to get units right. So that automatically makes all of those things extremely small, because you're looking at very, very small effects. There are, of course, certain people like Catherine Zurek who try to claim that you get, square root effects. But if your theory is actually Lorentz invariant, you cannot get those answers. They're just doing incorrect calculations.
Okay, any other questions or comments? Okay, if not, let's thank Surjeet for 3 very nice lectures, which will no doubt be very useful for students.
Yeah. Before we all split, I'd like to take this opportunity to thank Aninda and Loganayagam and the entire organizing committee that has done such an incredible job to put this school together. Thank you on behalf of the steering committee of this winter schools, which has been going on for a very long time now. Thanks a lot to everybody, the speakers and the audience. Thank you.
Okay.
I think you covered everybody, Aninda. Yeah. Thanks on my behalf.
Great, Loga. Thanks.
Thanks.
See you around. Bye-bye.
Bye.
Bye.